Good afternoon. Thanks for coming to this panel that I'm honored to moderate. I will try to avoid that it ends with a bloodshed here. I think there is little doubt that AI is undergoing a transformative phase. It is driven by rapid progress in machine learning, the emergence of agentic systems. I must say I hate the word agentic, but agentic systems, and the broadening impact of generative models. These developments raise many pressing and important scientific, technological, and ethical questions on the future of our field. And this is what we are going to try and address today. This panel brings leading voices that have dissenting opinions in some aspects about the next generation of AI research and applications. So we will discuss the evolving relationship between traditional logic-based approaches, or maybe symbolic approaches, and the new wave of agentic AI systems that combine autonomy, reasoning, learning. As large language models continue to dominate the research in industrial landscape, we will consider their developmental limits, both conceptual and practical, including concerns about data scarcity, a big critique has been made on that, redundancy, and quality. The panel will examine as well what constitutes a true breakthrough in generative AI, with examples from areas such as material sciences, drug discovery, we have some experts on these topics, and creative domains. We will revisit the foundational role of formal models in artificial intelligence. Are they obsolete? Should we forget about them? Particularly as complexity and opaqueness in current systems increase. What's the role of these formal models? Finally, we will address the ethical dimensions of AI development and deployment. I think this is unavoidable in all the discussions we have since, I don't know, I would say 5 or 7 years ago. We will discuss that. From fairness and accountability, societal alignment, and the implications of delegating decision-making into these machines. And then we may reflect about what Hinton said a couple of days ago. I mean, are the universities reaching their end? Should we close down all the universities? I mean, that's something for debate. My name is Carlos Sierra. I am the director of the Artificial Intelligence Research Institute in Barcelona. It belongs to the Spanish National Research Council. And together with me, we have, starting from that end, Edward A. Lee. He has been working on software systems for 40 years. He currently divides his time between software systems research and studies of philosophical and societal implications of technology. After education at Yale, MIT, and Bell Labs, he landed at Berkeley, where he is now professor of the Graduate School in Electrical Engineering and Computer Sciences. His software research focuses on cyber-physical systems, which integrate computing with the physical world. He's author of several textbooks and 2 general audience books, The Co-Evolution, 2020, and Plato and the Nerd, 2017. Very interesting title. So welcome to the panel, Edward. Then we have with us Ute Schmid, who is full professor of cognitive systems at the University of Bamberg, director of the Bamberg Center of AI, BaCAI, and member of the board of directors of the Bavarian Research Institute for Digital Transformation, Bidt. That's a bit more difficult to pronounce. Her research interests lie in cognitive AI, inductive programming, explainable and interactive machine learning. And Ute Schmid is a fellow of the German Informatics Society and IIIA fellow. For her engagement in supporting women in computer science, she received the Minerva Gender Equality Award from Informatics Europe on behalf of her university. Congratulations. She has been active in AI education for many years. In recognition of her outreach activities, she was honored with the Rainer Markgraf Award. Good. And finally, with a shorter CV, thank you, Michael. Michael Bronstein is the DeepMind Professor of AI at the University of Oxford and the founding scientific director of AITHYRA, a new biological AI research institute of the ÖAW, funded by the Boehringer Foundation. His main research interests are in geometric machine learning and generative models for biological sciences and drug discovery and design. So welcome to this panel. I will put questions. They will answer each question using a few minutes. Hopefully they will debate and punch one another. And then at the end, if there is time, we are going to open the questions to the audience, okay? Now, Let's start on one of the big debates nowadays on logic and agency. So how should we understand the relationship between classical logic-based AI approaches and the new generation of agentic systems? Agentic in the sense of using LLMs as one of the elements inside these agents. Are they complementary? Are they in tension? What do you think? Can be symbolic rigor of logic contribute to better alignment and transparency in agentic AI? What's the role there? What new formal tools are needed in order to model these complex multi-agent interactions of all these agentic systems in today's dynamic environments? We just learned that the Chinese have this other system where they put 12 AI models on a space connected through laser, communicating through laser. I mean, they want to span that to 2,800 different satellites. So this is becoming a reality, it's not science fiction. So please, what is your position on this debate?
Shall I start?
Yeah, please.
Okay. Well, I'd like to start by picking a fight. Is Toby Walsh here? Oh, good. I can pick on him. From the previous panel, I'm going to quote him. He said, "Computers do exactly what you tell them to do, and no more." Okay. So what I'd like to do is draw a contrast between logic-based systems and the LLMs first, and then secondly, the agents. So I think what Toby was reflecting is what I think is actually a pretty widespread misconception, which is that the LLMs are realized on computers. Computers basically do logic-based processing. They execute algorithms, which are step-by-step programs. They're designed by programmers, and therefore programmers are telling them what to do. And I think one of the things we've learned from the LLMs is that even the experts are surprised by their behavior, and certainly the programmers are surprised by their behavior. And as a consequence, the behavior is perhaps not usefully thought of as the result of a logic-based procedure. I think, but this misconception is prevalent. I guess, it shows up in a bunch of different ways. I love what Pablo Picasso said once, which was, computers are useless. They only give you answers. And perhaps a little more seriously, Abelson and Sussman, in their famous book, An Introduction to Computer Science, introductory book, they said that the computer revolution was basically about procedural epistemology, so knowledge through procedure. And when we talk about the algorithms, we're reflecting that it's really knowledge through procedure. Algorithms are procedures. I don't think this is the right way to think about what these machine learning-based systems are doing. I don't think it's a useful way to think about it. I think the fact that we're realizing them using computers is because it's a brute force realization, really a brute force simulation of a process that is really fundamentally not algorithmic. And as a consequence, I really think that we should draw a very distinct contrast between what the large language models are doing versus logic-based systems. And I guess one way to think about this, perhaps, is that in humans, Daniel Kahneman famously made this distinction between System 1 and System 2. And System 1 is sort of the quick, intuitive decision-making that we make decisions that are sort of inexplicable. Of course, we sometimes come up with explanations after the fact, but it's post hoc rationalization. And then System 2 is the logic-based processing that we struggle to learn and struggle to teach our kids. And a great fraction of the education for our kids is trying to get them to do that well. Herb Simon got the Nobel Prize for pointing out to economists that humans are actually not very good at this System 2 logic-based reasoning. And I think that we should be thinking of what the large language models are doing as much more like System 1 than like System 2, They're not doing logic-based reasoning. It's much closer to intuition.
Thank you.
Yeah, so I also wanted to refer actually to System 1, System 2, and making the contrast between knowledge-based systems, which are very much logic-based systems with explicit modeling of knowledge engineering, which had a bottleneck, which brought around one of the AI winters. Yeah. And on the other hand, the huge amount of implicit knowledge humans acquire, which is not verbalizable, often learning from experience, perceptual knowledge, like in medical diagnostics and so on. And I think machine learning, looking at classifier learning, which is around for a long time, and looking at Gen AI approaches, which are around a much shorter time, for both, I also would not agree with Toby Walsh, and I would say the computers do what the data say, right? And in the panel before this one, we had a longer discussion about the problem of biases in data, which is a problem. And I think another problem is that when you learn such models, be it a classifier or what is in a transformer architecture, you very much get a streamlining to the average, which I see a problem. So we also heard in the last panel, sorry for the repetition, but I think
I hope Toby is around, I mean, to answer these
some important points that, yeah, now I lost track. That human AI teams, that was the point. There is a meta-analysis from last year in Nature Human Behavior, where it has been shown that in human AI teams, typically the coming out decision or problem solution is worse than either for the best AI solution alone or the best human expert solution alone. Yeah? So I think we have a big challenge by combining the knowledge-based approaches, the machine learning approaches, and the human in the loop, or the AI in the loop, depending on your perspective. And I want to end with looking at agency. I also don't like the term. I think in a way we see a renaissance nowadays in rediscovering the use of knowledge-based AI and, for instance, things we had as methods in multi-agent systems in the 90s, like belief, desire, intention. When I want to assign a specific task to a specific software agent, I think these type of models, which are logic-based again, are back, yeah, and in general we need knowledge-based AI for augmentation of generation. I just give one last example. When you look at a machine translation, for instance, from English to German, and you have something like the cleaner hates the developer because she always leaves her desk dirty. When you translate this to German, you really get a semantically wrong translation. You can try it out. It's around since years, but there will be a male description of the developer first, and then a she, which refers to the cleaning person, which was not the semantic meaning of the sentence. And of course, you could use linguistic knowledge to augment generation to reduce these type of problems.
Yeah, very good. So please, your position.
So maybe I would like to make a distinction between, deep learning or machine learning-based methods, which I was asked to be more controversial. I think that's, at least currently, the only thing that works, at least on large commercial scale, versus maybe more traditional symbolic-based AI systems. And one of the reasons why deep learning has been advantageous is that if we take more or less any phenomenon, right, or for example, in scientific discovery or any process or any object, in some cases we can describe it mathematically in the form of logic, right? We can then, or differential equations in physics, we can then program it as code in software, right, and run on a computer, right? And in this case, I would actually agree that we could say that that computer does exactly what it is told to do. But in many cases, we don't have this possibility, right? So take even trivial examples. Take the problem of image classification. So we want to tell apart a cat from a dog. We don't have an equation of a cat, right? So it's very difficult mathematically to tell what makes a cat look like a cat, right? Or if you take a biological system, we might have an equation that tells us how atoms behave in a molecule. We don't have an equation of a cell, right? And probably there might be no equation of a cell, or at least something that we can write symbolically and a human can interpret, understand, manipulate. So in this sense, reversing the order, right? So not starting from some kind of logical model and then running it on data on a computer and then producing some output, but doing the opposite, starting with examples of behaviors of the system. And this is exactly how machine learning methods work, right? So they take as input some certain amount of data, what we call a training set, right? Examples of inputs and outputs, and then figuring implicitly the logic, typically in the form of weights of a deep neural network. If you have sufficient computational and data scale, it works well. And this works well for image recognition. It works well for physical scientific problems, like, for example, protein folding. The Nobel Prize in chemistry was given last year to DeepMind for AlphaFold. And it could be that in some fields of science, this is the only way to go. We might be out of problems which can be written symbolically. And it has always defied these gloomy prognosis that deep learning is running into the wall, and we are running out of data scale and compute scale, and every time it is defied. For example, now we have inference time scaling, right? So you can allow your model to think more, so to say, and then that's another dimension in which you can scale. So I think there is a lot steam in deep learning algorithms. Whether this is the only way to do artificial intelligence, probably not. And in many cases, we do have some kind of logical notions that would make, for example, significantly more efficient use of the data. So deep learning works when you have a lot of data and a lot of compute. In many cases, we don't have data, or the data is very expensive. This is true for scientific applications, especially in experimental, in life science. And in many cases, we do have some understanding of the world. So we do have some models. Maybe they're imperfect, so we can incorporate them as some form of inductive biases. So I actually, before this panel, I asked an LLM about what's the relation between the symbolic and deep learning based approaches, and I like the answer that this is unrealized synthesis. So it's a very diplomatic answer if you think of it.
Yes, indeed.
And very optimistic.
But I see some appreciation that maybe, at least for the Kahneman, I mean, there's some complementarity, but you also have this idea that some problems, if you have the knowledge, then maybe it's the best way to go. So there is no a dispute that cannot be solved, or that cannot be cooperation among both areas. That's my reading of your comments.
I think it's not common yet, but of course there are attempts to merge the two approaches, or neurosymbolic methods. There are some successful attempts, especially when there is a sense to the formal part. So one example is, for example, software generation, or automatic theorem proving in mathematics, where you actually have a formal verifier that can test whether your solution makes sense.
Okay. So if anybody from the previous panel wants to say anything now, that's fine. Otherwise, we can leave it for them. So let's move into another point, which I think already appeared.
Ricardo wants to say something.
Okay. You can talk at the end. Okay. About the limits of large language models. I mean, you already mentioned that a bit. I mean, the question is whether there are fundamental limits that would prevent this progress to continue. And so beyond computation and cost, which is an issue, what role do limits in data diversity and quality play? What is the role of this potential limit? And then can future improvements come from architectural changes? I mean, we saw this DeepSeek, for instance, with different elements in the architectures, or we are nearing the ceiling of the paradigm. We cannot, the last mile cannot be made. I mean, what is your thinking about that? I mean, in terms, if you can open that, if you want to a strong AI, I mean, is this the path to a strong AI, to general AI or not, or where is the limit?
Okay, I guess it's my turn again to address this first. I think that you know, the large language models are basically prediction engines, and the training data, for the most part so far, has been human-generated training data, and so I guess by analogy, you know, when we educate our young in school and so on, we educate them with human-generated data. So all of the mathematics that we teach them, for example, is mathematics that humans have figured out and written down in textbooks and so forth. And that's the same training data that we're using to train the large language models so far. And so I would say that to some degree the large language models are limited by human capabilities here because in effect the training data is reflective of what humans have figured out so far. And of course they have proven to be able to do occasional inferences that go a little bit beyond this, but it's always a little bit beyond this. And I think that it's kind of going to be an interesting experiment because an experiment that is very much underway where an awful lot of the training data is going to be actually have been created by the large language models of the previous generation. That is already happening, right? Almost, you know, any newly created web page or PDF file. I mean, people who write technical papers these days are heavily using large language models to generate text, to generate related work sections, all sorts of things. And of course, this is going to be the training data for the next generation. And this is going to create a feedback loop that I don't think anyone really knows what's going to happen with that. I think there have been some experiments that show instability in such feedback loops. Microsoft did some pretty interesting experiments where they were pitting two neural networks against one another to learn to negotiate. And they fairly quickly, they started out negotiating in English, but the language fairly quickly degenerated into something that was pretty unrecognizable to most of us. And yet it was actually effective for these machines to negotiate with one another. And so it's not exactly clear to me what will happen. I think feedback loops are intrinsically unpredictable. And so I don't know what will happen. Maybe they will invent new things that humans never would have thought of possibly. I'd like to also address sort of the flip side of this, which is limitations of the symbolic side, and maybe picking up on Michael's comment right where you said, I think quite rightly, that we may be running out of problems that you know are well suited to these kind of analytical techniques that fall within our bounded rationality to be able to manage. And I think for those of us who have a mathematical inclination, there's really a very simple proof that these algorithmic approaches have a very serious limitation, right? Which is, you know, the set of all Turing machines is a countable set, and there's no reason to believe that the set of problems and systems in the physical world is a countable set. In fact, it's almost certainly an uncountable set, and countable sets are infinitely smaller than uncountable sets. And so it would be truly remarkable if these algorithmic approaches were, in fact, as universal as your computer science professor will try to teach you.
Yeah, okay. I will take on what you said. We could also talk about strong AI or artificial
Yes,
general
please,
intelligence now,
please.
because I think many people who try out or work with ChatGPT and other systems tend to be sensitive to the so-called ELISA effect, like assigning even emotion, understanding, and so on. Of course, the AI researchers here would, I think, not do this. But I think AI as a toolbox is something very, very useful and powerful. And when we will talk about breakthroughs in the next round, I think we will see examples where it could go. But I think one limit is artificial general intelligence. I think this will only be just a not valid ascription to these kinds of systems, because some things are basically missing, which is like inner sensation, the qualia, an experience of things which cannot be realized by a synthetic system. Metacognition may be realized partially, like having an evaluation layer on top of a system. Intentionality, I think, will never be realizable, which is, I think, in parallel, there is the panel on AI and art. I think human artistic achievement is driven by an inherent intentionality, which such systems can't have. Don't misunderstand me. I'm a researcher in AI. I believe in the power of AI as a tool, but I think it's a wrong ambition to create an artificial general intelligence. Maybe another point where I see a limit, so in symbolic logic-based systems, we have relatively clear evaluation criteria, like proofs of correctness or completeness, or at least semi-completeness. In classical classification learning, we have the F1 score. You could debate maybe a little bit about whether this is always really a very valid tool, but up to now, I don't see a good way how to evaluate generative AI systems. What we see in papers is benchmarks and comparing the performance of LLMs against human experts. And maybe my co-panelists have ideas how to come up with a F1 score-like measure for LLMs. I don't see it, and I think it's a big problem. Because when you, for instance, use LLMs for, let's say, scientific discovery or code creation, it might give valid or correct or helpful outputs, but sometimes it might be not the case. And so for each and every output, in principle, you would have to monitor, because you don't know when the output will not be correct, desirable, or whatever. And I think that's a big problem and limit.
Okay, so maybe I would like to relate to the computability aspect, maybe slightly from a different perspective. So if you think of the sort of problems that we need to deal with in machine learning, so they are, at least in theory, are computationally intractable, right? And one of the reasons you can make it a geometric argument, because the input is usually very high dimensional, so you run into a phenomenon that is called the curse of dimensionality, right? So roughly the number of examples or the size of the training set will need to be exponentially large as function of the dimension. So even tiny images, for example, that you try to classify, you need to show more examples than the number of atoms in the universe. And yet we see that these methods work. And the reason is that machine learning works where your problem has a certain structure, or your data has a certain structure. I can call it the generate solution space. So where there is something in the data that makes all the solutions that are possible in theory not likely or impossible. So this is true for language, right? So in language, we have the phenomenon that on which LLMs are actually based, which is called the distributional hypothesis, meaning that words that occur in similar contexts tend to have similar meaning. And that's why we don't have an arbitrary permutations of words in a sentence, right? So they come in certain order that is dictated by the semantics and by the grammar of a certain language. This is also true in proteins, right? So when people try to impress you in computational biology, you will hear a number like 10 to the power of 300. So that's the theoretical number of proteins that can exist in nature. We don't see all these proteins, right? And why? Because they're a result of evolution. So evolution seems to be working in a lazy way. So a little thing that worked in one organism 3 billion years ago, it will be replicated maybe with some variations, copied and pasted in different organisms across different functions. So the practical number of these structures is orders of magnitude less. We also see it in images, right? So if you take images of cats and dogs, they will not be just uniformly distributed in the space of pixels, so there will be some kind of low-dimensional structure. It's often called manifold hypothesis in machine learning. In intelligent games, right, like chess or Go, we also have some kind of repeated patterns in software writing, right? We always reuse maybe pieces of codes or similar patterns in mathematics as well, right? So you can go on and on. First of all, these kind of problems, probably we can tell a priori or maybe post hoc when we solve this problem, like AlphaFold, right? We can look at it back and say, oh, this was actually an easy problem in the sense that it was well amenable for machine learning. And LLMs are just one way of doing it. So these are correlation machines. So they are very good at discovering correlations. Whether this is really what we want to do in knowledge or scientific exploration, we really want to find causal structures, and probably there is more than just LLMs. But probably there is a little bit also of this kind of, well, there is a term, hardware lottery, so in a sense it's software lottery. So with enough computer and enough data, it works well. And this is where all the field has put the emphasis and the money and the attention. Maybe I will just finish with two interesting technological trends. So we now see so far there was a very clear mathematical distinction between models that were used for language, like LLMs, right? These are autoregressive models, versus models that are used for example, image generation, right? Diffusion models or flow meshing or these sort of things for continuous data. So we now see the first emergence of diffusion-based LLMs, which not generate the output word by word or token by token. They generate everything at once. And this is interesting, basically borrowing methods from the other domain. Another interesting trend is that we now have so many checkpoints, so many models that you can find in repositories like Hugging Face, literally millions of them, that neural networks themselves have become a new interesting data modality. So we can design neural networks that take as input other neural networks, potentially train new neural networks on examples of existing neural networks. So there is an entire field of learning in the space of parameters, in the weight space of neural networks. Yeah, so it is interesting how maybe LLMs can be applied to LLMs rather than to human data.
Higher order LLM.
So,
yep.
Ask LLM, give LLM a program, let's say Python program, 1,000 lines of code, and ask LLM what is the answer.
Running the code on some.
It's to run it, right?
Yeah.
I don't think it can do it by stochastic completion.
It will probably not work. Yep. Yep.
That means it has
But-
it starts to become symbolic. To answer a simple question, it has to become symbolic.
yeah, but I think that that's a misunderstanding of what LLMs are good for, right? I mean, that we have much better machines for doing that. It's called a Python interpreter. It's a far better machine, uses much less energy.
But the point is that we should not think of LLM doing everything.
That's
Ask an LLM to multiply two numbers.
this is the mistake that people. I read an article just a couple of days ago where, someone was making fun of the LLMs because it asked it to create a table of all the 50 states of the U.S., the capital city, and the population. And there were a whole bunch of errors. Ha, 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 laughed at the machine because it made all these errors. We have had database systems since the 1980s that would answer that question perfectly. Okay? Why are you asking an LLM to do this? That's not what they do. That's not their strength. Ask it to generate the SQL query to query the database, and it'll probably do that flawlessly. Okay? But that's a different task altogether. So if I could introduce some controversy, I actually have points of disagreement with both of you.
Okay, good.
Oh, excellent.
Okay? On intentionality and on causality.
Okay.
Okay?
Please go ahead.
Yeah, so I don't think intentionality is so mysterious, actually, and I think that the machines are actually capable of a form of it. I like the term that Daniel Dennett uses for it rather than the Searle term, which is kind of mysterious and intimidating. Daniel Dennett calls it aboutness. Okay, and it's this idea that in a cognitive mind you kind of form a model of the environment that you're interacting with. I have a control systems background, and model predictive control is an old technique, and to me, it is a primitive form of intentionality because you actually do construct a model. And now, these days, you actually augment this by learning the model rather than constructing it a priori using analytical techniques, which is what, people used to spend entire careers learning how to deal with incredibly complicated, multidimensional, nonlinear differential equations to construct these model predictive control models. And these days, no, you just, you learn the model. And the key, I think, is that the machine, in this case, is engaged in an interaction. And interaction is fundamentally richer than objective observation or Turing church computation, okay? When you're actually interacting, you can, in fact, get at least a primitive form of intentionality. Now, whether that'll take you all the way to getting human cognition, I have no idea, but a primitive form of it, I think, can easily exist in these systems. So related to that is this issue of that you Michael commented that we're looking for causal relationships rather than correlations. I think that one of the things that absolutely blew my mind about the large language models, and I think surprised everybody else as well, was they're doing token prediction, and somehow they figured out numbers, the concept of numbers, and to work with the concept of numbers, and then actually to work with the concept of algebra. And yes, they made errors. People made fun of them, right? Give them a arithmetic problem and they do it wrong. If you just teach them to use the arithmetic hardware in the machine, then they could get it right. But they weren't doing that. Right? They're doing it using token prediction. How the heck does token prediction lead to a concept of numbers? It's truly amazing, right? And I think a big part of this is that, the environment that we work in does have patterns. And in fact, it is the patterns that we're looking for, right? It's not, so I have sort of come to the conclusion, I used to think that the foundations of intelligence were in logic and mathematics and deductive reasoning. I've kind of come to the conclusion from the evidence of the LLMs that the foundations of intelligence are prediction, and that logic is an emergent property that follows from prediction, and one of the reasons that it evolved is that prediction is incredibly evolutionarily useful, and logic and deduction helps us do prediction better.
Interesting.
Very interesting discussion, but you opened the can of worms, I think, with all these discussions. And you mentioned Penrose and Dennett and their beta discussions in the 90s, and Penrose saying that strong AI was something impossible to have because of quantum reasons. And so what would be your position? I mean, do you believe in a strong AI? And are LLMs the path to it? Very short. I mean, you can say no and no. And the three of you, I mean, it's just to see the opposing views. Yeah.
Yeah, I mean, I think that the jury is out. I think that we are seeing signs of a potential emergence of an intelligence that will have very human-like and perhaps exceeding human-like capabilities. I don't think we're there yet, but I think that the possibility is there.
Okay. What about you, Ute? You don't see strong AI coming?
No, I don't see strong AI coming. And coming back to your argument for intentionality, I would agree with what you said, but you also qualified it as it's only a part of what we see in intentionality in humans, right? And it's a very mechanistic perspective on intentionality. And so, I don't feel beaten by this argument, because I think intentionality has something more to it, and maybe there is part which we will never be able to explain, because humans explaining humans might be very difficult on the whole.
Okay.
Yeah.
So the answer is, I think I don't have an answer, and I think the question is wrong. And it's one of the reasons why I dislike the term AI, because we don't understand what intelligence entails, let alone what artificial intelligence is. And it's always by analogy. And we always have these analogies, what are considered the hallmarks of human intelligence, like playing intelligent games, or art and creativity, or the faculty of language, right, or the perception. So we have machines nowadays that in some cases work significantly better than humans in all of the above, right? So we have computers that play better than Kasparov in chess, right? Infinitely better than Kasparov in chess. We have generative models that produce images that win artistic competitions. We have self-driving cars. We have translation across any imaginable language on Earth without a dictionary. But we don't have artificial intelligence, right? It's a kind of moving horizon. And it's probably comparing apples and oranges. So we now have oranges that are very big and very orange and very sweet and very tasty. Can we say that an orange is better than an apple? Probably not, right? So it depends on how you compare, what kind of qualities you compare. So for me, the criterion would be really whether AI, right, whatever you call it, right, machine learning-based systems will be able to make non-trivial discoveries in knowledge, in science. Can AI win the Nobel Prize, right, or participate in a discovery that will be worthy of a Nobel Prize? I believe this is possible in the next 10 years, maybe.
Okay.
Yeah, so I think it's we're getting closer there, but whether to call it artificial intelligence or not, I think it's more a question of semantics.
Okay, let's move on and go to another question. On the breakthroughs of generative AI, okay, and their acknowledgement. So what are the most meaningful breakthroughs of generative AI so far? Okay, we can extend it to deep learning if that's preferred. And how do we define them, these breakthroughs? Okay, so how have these generative models impacted domains such as material science, like new compound discoveries that we know, software engineering like code generation, or art and design overall? And what sets these advancements beyond mere automation? Is there anything else apart from automating processes? Maybe someone else can start, and not always you.
I can try to start.
Okay.
So I think AI in scientific discovery will change the very way that science is done. Right? So if you think of how science has been working, well, for roughly the last 400 years, the scientific method has always been based on three stages, right? So you create a hypothesis, you use it to make predictions, and you test it experimentally, right? So Newton probably, right, his probably most famous work, Principia Mathematica, so exactly he created a mathematical model of planetary motions, made predictions, invented a new telescope that he used to observe the planets, right, or the celestial bodies, and he observed that his predictions are correct. So technology has always accompanied science, right, from the experimental validation, right, telescopes, microscopes, different instruments, you name it. Predictions as well, right, especially with the invention of digital computers. We nowadays do more or less everything in simulation. But the hypothesis generation has always been a human endeavor. So it has always been this eureka moment, the, I don't know, spark of genius, intuition, whatever it takes. And for the first time in the history of science and history of humankind, we have the machine that is not only a mechanical amplification of the human brain, but it starts taking creative part in this process. and it's hard to say where it will lead us. I think it will change radically the way that science is done. And probably the first field where this will happen will be formal sciences like mathematics, where we will see results that are entirely generated by computer without human help, probably to the extent that will surprise and amaze human mathematicians. We're probably not there yet, so again, better experts than myself in this field give it between 5 and 10 years. So the reason why I'm saying why mathematics is probably the first field, and it's kind of counterintuitive because it's considered the hallmark of human genius, right? So the purest of sciences. And the reason is that mathematical data is probably the most perfect and ideal for machine learning. There is no noise, right? So, and you can formally verify your solutions. So you can imagine a generative model, I don't know, an LLM or whatever it will be in the next years, that produces potential proofs of a theorem. You can very easily verify whether the proof is correct. And if it's not correct, you reject it, right? And maybe it will take 1 billion attempts before I get it right. But the moment I get it right, that's it, right? So this is what Terry Tao calls experimental pure mathematics. I can basically give it to a computer and sample my space of whatever solutions, right? So sample mathematics experimentally, and this way connect the dots. And probably it will excel in exactly in this business of connecting the dots, because mathematics is a very narrow and very deep specialization field. So experts in functional analysis have no idea about what happens in logic, right? There are a few exceptions. Tao himself probably is an expert in something like 5 or 4 fields, deeply in the way that he can produce novel results, but most of mathematicians are not. So connecting the dots, and a good example is, for example, the famous Fermat theorem, which required, it's a result in number theory, but it required completely different mathematical tools in order to get the proof. So this is probably where artificial intelligence will excel or will be useful, because it can absorb knowledge of all humans that no single human can have.
Okay.
But you said without any human input or support. In the end, you need a very, very highly qualified and specialized set of humans to evaluate, whether this new discovery of a theorem, for interest or proof.
I disagree. I disagree. You can do it totally automatically. So the humans are needed to provide the data. So this is currently still impossible automatically, but we're probably a few years away from formalization of mathematics. And since then, and after this is possible, it's number crunching.
But back at Hilbert. Back at Hilbert, who tried to formalize complete mathematics.
Well, but the problem with Hilbert, so the problem is that not every problem is solvable. But we are not talking about this. We are talking about within the constraints of mathematics, whether you can.
Yeah, but if I'm try again to get my point, maybe I see it wrong, but in the end, in mathematics, or let's say in scientific discovery of molecule structures or other topics, in the end, humans need to we use AI as a tool for human productivity in science and in business, right? And in the end, you need a human to decide, well, wow, this new structure of molecules, let's try and test it then really in the lab for a new medication or whatever.
Can I help here? Because actually, I think you're making a very good point, and I think you're not actually going to end up disagreeing. I think.
Okay.
So
we want this agreement.
So let me state the situation in a slightly different way, right? So one sort of naive way to view the problem in mathematics is to invent new theorems, right? So new theorems for which you have a proof. But given any formal system, you can write a computer program that will generate new theorems. Right, you just start with the axioms and start applying the rules of logic, and you can generate theorem after theorem after theorem and write this program that will just generate theorems out the wazoo and print them using all the possible paper that you could come up with, and the vast majority of those theorems will be new theorems that have never been published before by any mathematician or anything else. The problem is that the vast majority of those theorems are not interesting, and the proofs are not interesting. And I think that the truly remarkable thing that has happened with the large language models is that they can actually figure out which ones are interesting. Now, they're using the patterns in the training data to see that, right? So they've read all the math textbooks, and they know what all the classic theorems are, and they're able to map, some subset of this thing that they generated onto those classic theorems. And so they're able to highlight things that a human might want to look at, as opposed to just generating novelty.
Use the microphone, please.
The trees fall in the forest, nobody heard the noise.
Yeah.
Imagine LLMs are publishing thousands of math papers, and no humans have read them.
That's right. So
Have they done math?
So
Have they done math?
have they done math? Well, I mean, so one of the things that I complain about in my community is this obsession with novelty, right? The fact is that we can completely automate generating novel results, totally automate it, and no one will want to go to those conferences.
Yeah. Yeah. So.
But automatic theorem proving or computer-based theorem proving is not new, right? So the first result of this sort in graph theory and some coloring problem was already in the 70s.
No, but my point is, if you take the humans out of the equation, it's not math anymore.
Right.
It is not math. Math is a human activity.
So
they can publish thousands of my papers, nobody reads them, nobody cares.
So some mathematicians argue that this kind of 10,000 pages proof is also not mathematics, right? So it depends on whom you ask. Even though it proves the result, so from technical perspective, it is a correct proof.
But at least somebody asked the question. There was a human involvement. But now we're talking about with fully automated math. The question is it math?
This is a very anthropocentric point of view. What if the theorem is actually of interest to the other AIs?
Yep.
Let them. I can see a conference in the next 25 years, right? They will be a human digitalism.
Okay, very good.
There is a number.
So yeah, you want to say, yeah, please,
yes,
please.
If I may join in, sorry.
We are derailing already. Good.
I think there's something to be said about science that hasn't been that you didn't mention. Science is a human endeavor. I think it's, yes, a big part of it is about correct models and prediction and doing useful things, but that's not all that scientists do. A lot of scientific progress is about exchanging ideas. The Republic of Letters was, and it's not just for the purpose of getting things right. It's because it's a way of how, as Byung-Chul Han says, it's a decision about how we want to look at the world. So I think there is something going on that is deeply societal and deeply human, and it won't help us if AIs talk to each other only about that, because in the end, this kind of understanding needs to help us. It's our understanding and our decision. So what about this?
So this, what both of you said, is the point I was trying to make, actually. And your argument, taking, or both of you, to an extreme is these having, let's say, Gen AI write new grant proposals and other Gen AI systems evaluating the proposals. You know, in the end, the grant proposals are about what a group of scientists sees as a worthwhile endeavor for a new research project, right? And it's not an AI writing a proposal and another AI system evaluating. This makes a big gap between the reality we are living in and the digital world.
So my question is, how do we ensure that we keep humans in this loop? I mean, I think that's the essence of this mission here. right? Because I don't think there's anything fundamental in what's going on that's going to guarantee that we keep humans in this loop.
But doesn't that get to your question of intent, right? So if there is intention, it will drive which theorems are of interest or not. And if the AIs have intent, then we will have that. But so you have to put intent back into this.
So I think it's worth clarifying a point of confusion. One of the reasons I don't like Searle's term intentionality is that there's two ways to spell it. One of which talks about intent, but that's not what Searle is talking about. He spells it with an S instead of a T. And Searle's intentionality is not about intent. It's about mental models of your environment. So I think you're right that intent is certainly an important thing, but that gets us into a whole different question, which is one of, can AI have goals? Can it have will? That's a whole different question. And I think that's an interesting question, but we haven't gone there.
But maybe, Beck, I want to clarify my point about, we were asked to be controversial, so I tried to do my best. So I personally don't believe that humans will disappear, so this is probably an extreme corner case, and you can argue whether it's still mathematics or science. Probably a better metaphor to think of it is a new level of abstraction, right? And if we take software as a metaphor, 70 years ago, we wrote software in binary code, right? And then came assembly languages and imperative programming and object-oriented programming. Nowadays, we can almost write it in plain English. And we are probably a year or a couple of years away from complex software products that will be written without any coding, so potentially opening up software development to non-experts, right? So does it mean that humans disappear? No, they still have the, intent or whatever you call it. So telling what is interesting and what has to be done. Same thing with drug design, right, or material generation. Somebody has to say, I want a material with these properties and with these, with this use and so on. Whether it cannot be, this part cannot be automated, I think it can. But humans will not be out of the loop probably, or at least for the next decade or 15 years or so.
So I think the last intervention, and then we'll recover the field. Yeah.
So because you mentioned the anthropocentric view, I read an article who's really went to the next level, that AI will in the future be able to do and decide their own research. So what they found, so in 5 to 10 years, they agree, or without human intervention, what they want to research and deliver the results. So I know this is very, very, but I think it might be possible. I just wonder, because you come with the mathematics, it's a very narrow field, but what if then?
So there is a science fiction novel, and I don't remember who the author is, but probably it will be easy to look up, also about this kind of near future, where AI scientists are totally autonomous, so they develop their own language to communicate, their own protocols and channels to communicate, and humans are studying with their primitive human scientific methods actually how the heck this thing is working. And they're producing results that are totally inaccessible and not understandable by humans.
But maybe one last argument for that. Okay. Coming from software engineering to architectural engineering, when an AI system would design a building, a ceiling, and so on, typically we hope that human experts who know what they do prove that the statics is right and the ceiling will not come down, or a bridge, yeah? And when I think this question of correctness, yeah? We all know that correctness is a semantic question, which is outside the syntactic computation. Wouldn't you agree? And I think in the end, you need a human expert on this semantic level to make a proof of correctness. And I think it's a big, big difference when you use Gen AI for end-user programming, which is
so in your architecture example, I disagree. So
again,
it's not a formal verification, right? Okay. So it's not a mathematical proof. You usually would do a simulation, right? So a simulation is not a formal verification. It's something that provides you reasonable certainty that it will not collapse.
Okay.
Right? But it's not a 100% bulletproof guarantee. in fact, buildings do collapse because even though humans presumably somehow verify that they are correct, right?
Okay.
I think that also correctness is a property of models, not of physical systems. And so I actually do think correctness is formally derivable and provable by computer from that perspective. And so I think usefulness is a different question, right?
Okay.
Let's recover a bit the discussion on formal models. I mean, we are living in this world where we have plenty of black boxes in which it is very difficult to get inside and know what is going on there. So what is is there any role for these formal models in AI? I mean, how can we really integrate those models with these data-driven approaches? I mean, is there still a role for formal models in AI?
I would say absolutely. I mean, I do a lot of software development, and I can't go back. I can't do it anymore without the help of the AIs. It's incredibly helpful. But when the AI generates a chunk of code, if you don't run it past a compiler, you don't know whether it's syntactically correct immediately. This is not something that a human eye can tell very easily, and so having the large language model generate some code and then running it through the compiler is exactly a partnership between two very different technologies, one of which is symbolic, which is the compiler. It's a strictly formal thing, right? It checks syntactic correctness and translates the program into a new form. And the large language model, which is definitely not doing anything like that, right? And that partnership is extremely powerful. And in fact, I think the real revolution that we're starting to see with these agentic systems, which I agree with you, I find the word incredibly awkward, right? But what it means to me is to make a distinction between a purely reactive AI. So a purely reactive AI, you give it a stimulus, it gives you an answer. You give it another stimulus, it gives you another answer. An agentic AI engages in an interaction, and it produces an answer, then does something with it in its environment, and then takes the reaction that the environment provides and then does something else. Well, one of the environment components that you can provide to these agentic AIs is symbolic systems. So for example, if you want to make an AI that never gives you the wrong answer when you give it an arithmetic problem, just teach it to use a calculator, right? The calculator is a symbolic system, and you program it as an agent. You ask it for not to give you the answer for this arithmetic problem, but rather to give you the sequence of commands to the calculator, have it invoke the calculator, and then interpret the response, and then give you that response. That's a perfect partnership. This is how humans work, right? We don't try to do fancy arithmetic in our head either.
Very good.
Yeah.
Views on this?
I totally agree with this view of the future, I think. And if, by extension, if we take it to experimental sciences, probably the lab itself where you do experiments will also be automated, and in order to verify whether, for example, your drug design or material design actually does what it's supposed to do, the LLM or whatever, the agent that runs this design will need to do an experiment and feed the results back into whether to improve it or modify it in some way, or whether the answer is satisfactory.
So I see that you both argue very much for agentic. We don't like the term, I agree. LLMs, where you decide for which type of problem, what is the best tool or approach to use. But I think it's also interesting to look at novel neurosymbolic architectures, not letting transformers with some add-on be everything, but really combine machine learning on the level of deep learning, let's say, with, let's say, inductive logic programming, learning symbolic rules on a top level, because these symbolic rules are much easier to interpret, to communicate, to control. And so one architecture proposal I like is from Luc Deraat from Leuven, deep problog, where he uses a deep learning model for classification of more perceptual tasks, let's say number recognition or something like that, and combines it with discovering, let's say, rules for arithmetic on the level of inductive logic programming. And you could use explicit knowledge representation in addition. So I think you would have a really interesting architecture. So I believe you could say, let's solve everything with LLMs, diffusion models, but I like these combinations of more symbolic, explicit approaches with deep learning and Gen AI.
So there's another example of a real success case in this combination, which is this technique that is now quite widely used with the LLMs called chain of thought, or COTS. Yep. Right? This is actually part of what makes DeepSeek as effective as it is, despite being a significantly smaller model, is that it's programmed to actually give you a chain of reasoning, right, using a certain amount of logical deduction. And one of the things that I find really amazing about this technology is how much it has the potential to give us insight about human reasoning, right? Because humans also do a better job when you ask them to explain their steps, right? Any math teacher in high school will tell you that, right? You tell the students, give me your steps, don't just give me the answer. And the students do a better job when they do that, and so do the AIs.
Well, this connects a bit with another question that we have, and I think is very dear to you, is about explainability. I mean, and how can we advance the development of AI systems that are at the same time, I mean, explainable but also meaningful to human beings? Maybe you can illustrate a bit that aspect.
Yeah. So I think also in the panel before us, or at several occasions here, we heard that also humans often explain on the hindsight, and explanations might be constructed justifications and not faithful to the real origin of what we did, for instance. So I would agree with that. Nevertheless, I think that explanation is a crucial building block for systems where we have human AI teams. And I think we all agree that for most applications, not all, but for most, we need human agency and oversight, which is one of the core requirements for trustworthy AI, which has been formulated in the context of the European AI Act by this high-level expert commission on ethics of AI development. And I think it's a big challenge to come up with a toolbox of different methods how to explain, which should be as rich as the best humans can explain. So you definitely not only explain with feature highlighting, which is a very nice explanation method to recognize overfitting, for instance, when you have image classification. But I think very often we are good with explaining with a near-miss example, a very important type of explanation in education, or with on the level of concepts, really give concepts and relations to make an explanation. For instance, you might say in industrial quality control, if you would just highlight some bubble or blowhole in a metal, yes, okay, if this is highlighted, you know something, that the model is not right for the wrong reason or whatever, but you wouldn't be able to explain, yeah, I classify this part as a waste part because this blowhole is on an important part of my piece which I construct. Yeah, so you need spatial relations, you might need temporal relations, and so on. So I think there is a lot of challenges still for XAI research, which are important for human in the loop or AI in the loop approaches. And I think one of the big challenges is that we don't only want to have explanations for understanding, let's say, of a human expert who interacts with a system, but also for model revision. Because even if we train a classifier with 99% accuracy, which is utopic in many domains, yeah, you need a possibility to make interactive learning human in the loop feedback for model revision. And to do this in a guided way, you also need explanations first. So it's not only explain to understand, but also explain to revise.
I think you have a lot more faith in humans than I do.
I have lots of faith in humans. Still.
There's a reason. There's a reason that the U.S. Supreme Court these days comes up with very good explanations for decisions that a U.S. Supreme Court 20 years ago would not have made. And I think humans are really incredibly good at this. And one of the tools that we're developing is giving them explanation machines that will help them. So the human will decide what is the outcome I want, and we'll go to ChatGPT and ask ChatGPT for an explanation for this outcome given the inputs, and get a whole bunch of really, really good explanations for that decision, and bam, you got it.
But this
and how is that? How is having the human in the loop better in this case?
But this is not what XAI is about. XAI generates an explanation why a model generated or produced a specific output, and
so
the explanation needs to be faithful to the model, which is a big challenge methodically. You talk about explanation generation in general, which is, I think, a different level than what XAI is.
I've done this experiment. I've taken legal cases and fed them into ChatGPT and said, give me an explanation for a convict.
Yeah, okay.
And then give me an explanation for an acquit. And you get damn good explanations for both.
But if you take something that is slightly more, let's say, exact science than legal field, so if you take physics, right? So what is explanation, right? So what is explainable? Typically, physicists want to have a formula, right? So a differential equation, like Newtonian mechanics, right? So very simple formula that we teach at school, right? You can understand exactly what I don't know, 3 degrees of freedom, right? Or 3 objects that we're manipulating in one equation. If we were to discover these from the data, take trivial phenomena like friction. It will probably be an equation with tens, if not hundreds, of different coefficients. Now convince me that this is more explainable than a black box with 100,000 parameters, right? So it's the fact that we can asymptotically ignore some of these parameters and reduce it to some specific cases is remarkable, probably possible in some cases, probably impossible in general. And we do we throw away important stuff that doesn't matter in some situations. We don't often understand when this is possible, right? So Einstein, the genius of Einstein was to understand actually when Newtonian mechanics doesn't work, right? And that's why it has become a new and interesting theory. So basically, to your example is we have a black box that we don't understand how it works. It works very well. It ticks all the boxes of a valid theory, right? So that's what Chris Anderson called post-theory science. So the famous Wired article at the end of theory in 2008. It is not human understandable. It is valid science, in my opinion, or in some opinions. And we need probably to revisit what we even call interpretable or understandable results, right?
Maybe, because I would like to give the audience the opportunity to talk. So we are going to do in the next 3 minutes your position on ethics. Something very simple to give in 3 minutes, I'm sure. So, I have a colleague, Tony Belpame, working on social robotics, and he claims that, actually LLMs are not bad at recognizing social values and so in the dialogue and interaction. So how do you think we can add this social value dimension into artificial intelligence, and why is that important? Very short, and then we move to the audience.
So some Republicans in the U.S. have claimed that ChatGPT is a Democrat, and my interpretation of that complaint is that it actually shows some ethics. But in fact, OpenAI went to considerable effort to actually make that happen. Right? There was some fine-tuning of the model that was human-driven, right? And there was guidance through this whole process to establish what really amounts to an ethical framework. So, from this perspective, what is ethics? Training data. That's what it is for humans as well.
Okay.
Okay. First, there should never be moral machines. Yeah? Why? Because I think morality and what is fair or just is something deeply human, which needs to be discussed and be agreed upon in a broad democratic discourse, right? So that's the first point. A machine can never be moral, and what fair and just is culture dependent. Yeah? So trying to train an LLM to have the morality of Austria culture, US culture, or whatever, I think is nothing I would want to achieve. I think morality belongs to humans. The second thing is CO2 footprint. Nowadays, most of LLM applications are in marketing and customer communications. Think about this ridiculous amount of energy to double or more your social media posts about a product which is rubbish and nobody really needs. This is ridiculous. Okay. I think using LLMs for scientific discovery, for code generation, for complicated parts, and so on, are all very interesting and worthwhile applications. Yeah? But everybody uses LLMs for lots of things. So lots of PhD students, for instance, use Netbook LM, which has incredibly high amount of computation, needs incredibly high amounts of computational resources. And I think when you do apply these big LLMs, you should need a certificate similar to when a pharma industry needs animal testing. There are very high standards when you are allowed to use test animals in whatever drug discovery in medicine. And I think we need the same for use of LLMs. Last point, education. Yeah? When we don't educate humans early on to be to be resilient against all this nudging we experience with social media, to not be able to evaluate quality. Yeah, we had the example this morning with the fast food, the processed food, and real food as an analogy. Mm-hmm. When we don't do this, I think the next generations will be very, very open to manipulation on every level.
Can you just say very shortly?
Well, I agree with more or less with everything that has been said, but probably one important consideration about AI in general, right? In education and in everyday use. So what scares me is overly relying on these systems. We will lose essential skills. And these are not necessarily mechanical skills, these are cognitive skills, right? And we see it in our civilization, we see it happening all the time. So some skills on which we relied for centuries for survival that were essential now are totally lost. So how many of you can ride a horse? So just very, very little, right? So, and this was just a couple of 100 years ago. I can do as well. So it was essential. So we literally, our life and death depended on this, right? Or produce fire and so on. So basically, we're giving away to technology things that are essentially human.
Start preparing your questions, then a final yes, no answer. Do you agree with Hinton that we are going to close universities down in the next 10 years?
I don't agree.
I don't agree.
I think universities will look differently, but I don't agree that we'll need to close them.
Very good, excellent. Okay, so the microphone is around. I mean, please.
I was sitting closest to the microphone. Maybe.
So you will keep your jobs. I mean, relax.
Thank you for the entertaining discussion and panel. I would like to argue that maybe trying to locate things like agency and morality and responsibility in the different kind of actors that we have now with AI and humans might be a wrong-guided discussion. And you know, you were asking like who's doing the math, and of course we weren't doing the math without like pen and paper. And pen and paper weren't not the passive tools either. The kind of math that we do depended on the technologies that we gave ourselves. And in that respect, also today, you know, we think about the kind of different relationships that we have to all of these technologies. They make us to the humans that we are. Right? And so it might be kind of very natural for us to think about, you know, who has what in that relationship. But the crucial thing is about how do we actually configure that relationship to become the humans that we want to be. And you know, there's a lot of like history in science and technology studies that has understood this importance of relationality for a long time. A lot of post-human theory has been grounded on that insight, that it's the relationship and not the entities that make that reality happen. So I see we do a lot of like positioning ourselves against something. Is it that, or who is doing what? And I think that's not very useful, you know, direction of that debate.
Can I just maybe quickly respond to this? So AI is not a force of nature, right? So this is technology as we develop, we shape it. So it's up to us, right? And us in the broad sense, society, politics, I don't know, whatever considerations, how we will be relating it, how it will be used.
So, other questions?
So to respond quickly, I don't think it actually is up to us. I think it's an evolutionary or a co-evolutionary process. But I do want to say that, you know, I mean, ever since the Sumerian invention of writing, technology has always been an intellectual prosthetic for humans, and it continues to be. And I think that the whole mission of this digital humanism initiative is precisely to make sure that it doesn't run away without us.
Okay.
So I sort of was just reflecting on that statement about not wanting to build moral machines, but the machines that we do build do have moral consequences. So I guess the question is how much do we engage in the engineering of those consequences? And maybe one of the things that we haven't really engaged with is how do we represent things like values and principles in those machines and actually explore those consequences. So we fetishize the strengths and the opportunities that some of these sort of drug discovery machines produce, but we sort of shy away from the negative consequences. And I think we need to be able to explore both those consequences when we're building these things. And I think that is part of engineering, and it is part of the building of these machines, even if we shouldn't let go of that agency for them to have those consequences. I don't know if it's worth having.
Yeah, I think it's worth injecting a word of caution, though, which is whose values. There's certainly plenty of humans whose values I do not want to see reinforced by the machines.
Yeah.
Yep, please.
Yeah, the vast majority of problems that we are going to see LLMs solving in the future are not going to be ones that have physical properties or provable theorems. They're going to be social problems. And I think this goes back to one of the principal challenges that we have with AI right now, and that's the ability to be able to watermark synthetic data. That the moment that synthetic data starts to become the beginning point of a chain of reasoning, you start creating a model in of itself, which, as you say, has this feedback loop. The challenge is that for a first generation, where we still have enough tacit knowledge in order to be able to establish what we mean by a fact that works. The moment you start moving into second and third generation, meaning our kids and others, we start to lose that thread. And that doesn't just distort reality in the way that Professor Lessig was saying, it actually breaks reality. And I think that's a huge danger that we haven't really explored. Thanks.
That's a very good point, I think, but I want to extend when GPT 3.5 has been trained by this crawl of all available information, right? There was neither a respect on copyright, nor was there any quality control. So what the GPT 3.5 really impressed us with was its impressive way to master language, right? But of course, there was a lot of rubbish with respect to knowledge I would guess, in a domain like medicine, where you have lots of also esoteric stuff on the web. I would claim that the smaller proportion in GPT 3.5 was really seriously validated information, and most was rubbish. So it's not only synthetic data, but also data quality in general, I think.
Here's another question down there.
Yeah, thank you. I want to come back to the discussion about mathematics and what research will look like. And I was thinking, we do have impact on that, no? As scientists, we can say this is the funds we give and this is the funds we don't give. And I was thinking if this is really what we want research to look like, to just be content moderators of research that AI does. We see that in other parts of not research, but of society, that people or highly skilled work becomes low skilled content moderation work, or not low skilled, maybe that's the wrong word, but work that we don't value in a society, and that is maybe what we become, just looking at equations, looking at things that we do. And I wonder if that is what you think we want to be as scientists, because I want to be creative in my science. I don't just want to check up on something that AI does. And yeah, I was wondering what your
So we probably have one example, right? And this is chess, right? So computers nowadays are way better than humans. We still have grandmasters in chess tournaments, so it didn't disappear because it's not interesting to look at computers, how they play with each other, right? So it might be the same for science. So when the science is right? So ars gratia artis, when it's for the sake of the process, when it's for the sake of discovering something and using it, then maybe AI will be considered a more efficient option, or maybe in combination with humans.
So Kasparov wrote a book where he essentially makes the statement that the machines enriched the game of chess for humans. That the machines taught us a bunch of things that no chess player had ever really thought about doing it this way, and that's sort of the basic theme of this book. And so I think the machines can be thought of as a cognitive prosthetic, and they can be an enhancer. And I think I agree with your goal. We want to use them as enhancers, not as replacements.
Thank you. Another question?
Hello. Thanks a lot for the nice discussion. I wanted to add that I missed a word that wasn't mentioned. I trust in AI much, much more about being correct about the mathematical thing than someone working in statistics. But what I missed is the word accountability. We won't get rid of translators or lawyers or someone because we need a person who will be responsible if there are mistakes made. So maybe this is also a question. Do you think that at one point we will give up the accountability to a machine? Is there a point where we will make the engineers responsible for what the machine did?
It's more a social agreement, right? So maybe in this generation it sounds unimaginable or very strange that we'll be giving accountability to a machine. Maybe to our children it will be totally normal. I don't necessarily, again, this is my totally unprofessional opinion. I don't see this necessarily as something controversial in the maybe next couple of decades.
Okay. I just want to use the occasion to tell you that if you are interested in the technical side of digital humanism, there is another conference here in Vienna, November 20 and 21st. It's just also here in the Museumsquartier, and it's also called Digital Humanism, and you find the announcement already on the webpage.
Thank you. Please join me in thanking the members of the panel for this interesting discussion.